Thanks a lot. So as I said, a tree is an undirected, cyclic, connected graph. And well, we'll consider actually a special type of trees, which are called binary trees. A binary tree, well, the definition the book gives is kind of a recursive definition. So a binary tree is a structure defined on a finite set, on a finite set of nodes, which are the vertices of a tree, that either say contains no nodes or is composed by three disjoint sets of nodes which we call, say, root node, a binary tree called left subtree, and another binary tree called the right subtree. So essentially, a binary tree is a structure that we say, for which we sketch a graph like this. Could be something like this. So for every node, there are no more than either 0 or 2 children, and so we have a situation like this, or it could be something like, for example, say between 0 and 2. What is called a complete binary tree so the nodes, say, for which, sorry, the nodes for which there is, so these are called the internal nodes, and these are called leaves. This is probably a terminology you already know. And a complete binary tree is something like this, when you have either 0 or 2 children for every node. I'm quickly reviewing everything. Yes, and for a binary tree, what we have is that we define what is called the height, which is, say, sort of the vertical size of the binary tree. So in this case, the height is, say, from the leaves, if you go back to the root, which is this one, you have to jump, say, up by 3 levels. And so in this case, the height of the root, usually called h, is 3. And the size of the tree is the number of vertices. sorry, about what is the difference between the binary tree and the complete binary tree. Well, a complete binary tree is a binary tree where there are all children have either 0 or 2, sorry, all nodes have either 0 or 2 children. Okay, so this is a complete binary tree. We will see that actually the structure we are going to define is a, say, quasi-complete binary tree. And of course, the number of nodes, which is usually denoted by the letter n, is, well, the size of what is called the size of the tree. Okay. So, and now we move to the definition of the structure, which is a heap. So a heap is a data structure that allows for the representation of a matrix in a binary tree, say on a binary tree. So, sorry, of a vector on a binary tree. So what we are considering is, say, an example of a binary tree, like, say, we have an array A, which is, I'm taking this from the book, is, say, 16, 14, 10, 8, 7, 9, 3, 9, 3, 2, 4, 1. So this is an array of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements. And the idea is that we can represent an array, any array, in a form of a binary tree by using this, say, representation. We start from the first element, and we name it the root. And then we start by adding children to every node, say left and right, considering that we are using a binary tree. So we are just using, we can define only, say, 2 children. And so we have 14, say, on the left, and 10 on the right. And then, again, from 14, we start by 8, and then 7. And then from 10, we start, the left child is 9, and the right child is 3. And then we have under 8, 9, 3, we have 2. And then we have 4. And then we have 1. And this representation, of course, goes from top to bottom, from left to right, and corresponds. I'm using the numbering that is in the book, Introduction to Algorithms, with that starts from 1 instead of 0. Of course, you have to adjust for the, say, the Python representation, which starts from 0. So this is element number 1. This is element number 2. This is element number 3, 4, 5, 6, 7, 8, 9, 10. Okay. So what you get out of this, Professor, do we have lecture notes for today's material? Actually, what I did, I must confess, is kind of, kind of rewriting just for my, as a sort of reviewing the chapter 6 in the book. I don't know if actually chapter 6 is available online. I remember that some years ago, I asked the guys at the library about making available just a chapter of a book, and they did it for free, say, because of an agreement with the publisher. So I think this can be done as well, but I hadn't the time to use this. Anyway, I can give you my notes. I mean, they are not, say, very carefully written, but it's mostly, say, a copy and paste of the text of Introduction to Algorithm with some minor changes. So yes, anyway, I will give you some references, but this is not, I mean, apart from, say, the structure, this is, sorry, this structure and most of the things that you see, say, online are mostly correct, because this is kind of a structure that is very common for applications. Okay, so this is the representation of the array into a binary tree. And as I said before, this is a almost complete binary tree, because it's not actually complete because of this. But you see that the entries are, and we are filling the rows of the binary tree starting from the left. So at some point, we will never go down. We start filling the rows of the binary tree horizontally, and then when we reach the end, we go to the next row. So the height, so this allows for a number of easy computations to do on the tree, because for every, you see that, well, in this case, the first entry in, say, the first node on the left is 1, 2, 4, 8. So of course it is a power of 2. Okay, and this allows for some simple, say, computations, as I said, on the tree, because well, the root of the tree is, of course, a sub 1, which is that one. And for every entry, we can immediately get the left child and the right child and the parent, if there is a parent. Of course, the root has no parent at all, by just looking at the numbers. So the formulas are, well, we define the, say the parent of node I is simply I divided by 2. Of course, this is an integer division, okay? So the parent of this is 2 divided by 2 is 1. The parent of this is 1, because 3 divided by the integer division, we get 1. And you see that we always get, the rule is always true. Of course, you can prove these things. And for every node, you also see that the left child is 2i, and the right child is 2i plus 1. Okay, so the left I is 2i, and the right of I is 2i plus 1. Just a mention about the computational issues here, which is, I mean, all these operations, integer division, multiplication by 2, and multiplication by 2, and addition to 1, are easily performed by a computer, because in a representation of a binary code, these are just right shift or left shift of the binary representation. So they are quite efficient. Yes, please. Yeah. Yes, you have to adjust for the numbers. Yes. Yeah. I mean, this is the advantage of using. So I guess the guys, I mean, chose. I mean, of course, well, there is a problem, because we usually, mathematically, you describe entry starting from 1, 1, not 0, 0. So the top left entry in a matrix is A 1, 1, and so this is say, a frequent issue that arises. Of course, you have to adjust for some of, say, yeah, 0, 1, yes, yes. Sorry, we mean right or left relative to the position of each node, or relative to the topology of the graph? No, to the position of each node. So this is right of I. So you take any node, say 2, and you want to get the right children, so you multiply 2 by 2, which is 4, and you add 1, and you get 5. And this is the right child of 2, so of 14, okay? So this is the way it works. Now, why is this structure efficient? Because, well, the idea is that we want to keep, say, an order on the array, an order based not on the array, on the positions on the array, that is on the indexes here, but an order based on the structure of the tree. This is an example. This is actually the example of the book. This is an example of what is called a max heap. So the whole idea is called a heap. Sorry, I didn't say that, which is the main thing. The structure like this is called a heap. And this is a max heap. Why max heap? Because every node is greater than or equal to its 2 children. Okay, so 16 is greater than or equal 14 and 10. 14 is greater than or equal 8 and 7. 8 is greater than or equal 2 and 4, and so on for all the other nodes. Okay, and this is called a max heap. So for a max heap, the main property is that A of the parent of I is greater than or equal A of I. And of course, in a max heap, the maximum of all the entries in the array is the root node. There is also another, again, I'm following the book, of course. The presentation is done with max heaps. But of course, there are min heaps. Min heaps are just, say, heaps that are organized in such a way that the parent is less than or equal instead of being greater than or equal. And so in that case, in a min heap, the root is the minimum of all the elements in the array. No, no, exactly as in this case, this is not necessarily. So of course you could swap, say, 2 and 1 and it would be exactly the same. As I said, the property is this one, the key property, okay? Well, it's like, consider this, which is of course a binary tree. Well, in this case, it happens that, yes, it happens, but could be like this. And yeah. So, so there is another thing that relates, which is important for what we are going to say. Another thing that relates the number of entries with the height of the tree. Now, the height of the tree, you see, is measured by the exponent that you must give to 2 to get at least the first element, okay? So it's 0, 1, 2, 3. And this is actually goes more or less like the logarithm base 2, which, say, apart from a constant, is whatever the logarithm, the base is a logarithm of n. So if you take the logarithm of n, say, think of, if you want base 2, you get the height of the tree. So in this case, you have 10, and the logarithm of 10 base 2 is 3 and something, because the 2 to the third is 8. And so you get the height of the tree based on log n. So essentially, we have that the height of a tree is log n, at least big O of log n. So you know that when, say, we are doing computational analysis, complexity analysis, computational complexity analysis, we are not worried about constants. So this is what relates the two quantities, the height and the size of the array. Okay? Yes, of course. Well, you should say something like, if you like this. Okay, so yes. Is it n is the number of nodes? Yes. Or if you want to see it, is the, well, this is usually called the size of the heap, which is the size of the array. Yes. Okay. So let's see now. Of course, in general, when you start from a tree, well, this was a special case, but aren't the nodes 8, 9, 10 at the same level? Yes, they have the same height, of course. But we are interested in having a relation between the height of the tree and say the entries, the number, the size of the heap. Sorry, the height. Yes, which is h, which is log of n. Because well, actually, the algorithm that we will see are actually going, say, upwards or downwards, and so we are actually counting the height. So the way the number of steps we take for going upwards to the root or downward to some leaf. Okay. Okay, so in general, when you start with an array, any array, of course, and you put the number in a tree like this, you are not so lucky as in this case. Well, in this case is already organized as a max heap, but in general, you have not, you are not in such a situation. So the next thing we are going to talk about is how to maintain the heap property. Because of course, when you have the heap property, there are some things that you can immediately get for free, which is, for example, is the maximum of the array, which is the root. Okay, but in general, you don't know, and so there is an algorithm which is called, I'm following the, again, the book, which the book called Max Heapify. Which takes the array A and a position I. So what is the Max Heapify doing? So first of all, the assumption, we assume, well, A is an array, and of course, I is an index into the array. And then we also assume that the left tree rooted at AI, at index I, and the right tree rooted at, sorry, not I, but left eye, yes. Sorry about that. These things are much more clear if you, well, which is what I'm going to do, if you show them with numbers. At left eye and the right 3. Rooted at right eye are max heaps. Assumes that, but AI might be smaller than its children. So in this way, violating the max heap property. So the idea is this algorithm, the algorithm that I want to show you, works in this way. You are at a node, say in the tree. Say you are here, for example, this is I, and so you have a left subtree which starts here and the right subtree which starts here, and you don't know, say you might have many nodes here and say like this, say, well, of course, if you have nodes there, then it must be that you have nodes also here, something like that, okay? So I'm not filling the whole thing. So the idea is that you assume that maybe this is sort of wrong because it's less than at least one of its two children, but the left subtree and the right subtree are both max heaps. So they are okay by themselves, okay? So this is the maximum of what is below this, and this is the maximum of what is below this, okay? And you assume that, say, this algorithm just takes this and fixes this special case, okay? So, well, let's see how the algorithm works. And then I'll show you an example of this. I think I have an example of this. Yes, is this one. A1 is changed. Yes, is this one. And this is heap sort. And this is build max heap. Yes, so it's this way. Okay, so let's review the algorithm. So max heap AI. So first of all, we said L equals left I, R equal right I. And then if, well, if L is less than or equal to the size of A, which means that the left is indeed an entry in the tree, and A left is greater than A I. Yes. Then largest equals L. Else, largest equals R. And then if R is less than or equal A size, and AR is greater than A largest, it's greater than A largest, then largest equals R. And then if largest is not I, then, and this is the final thing, exchange AI with A largest. And then max heapify A with largest. Okay, so let's say in theory, what is the, so this is I, this is L, and this is R, I mean, as, say, the indexes. And so the first thing we are doing is, well, we want to be sure that the heap property, the max heap property is true. So what are we doing? Well, we don't know, because maybe, well, we know that below this there is a tree which is satisfying the property. So this is a max heap, and this is a max heap. Well, we don't know whether the value, the key here, is greater than the two values here or not. So the main part of this algorithm is just looking for the largest value. Okay, so it looks first for the left, and then of course to the right, and then, well, there are essentially two cases. Either the largest was indeed I, so in this case, of course, you do nothing, because the already the largest number is in the right place. But if it is not, then what you do is exchange the largest with the with I. So you either swap these two or these two, and now, of course, you are, this is larger than this. So say, for example, you have, I don't know, 10, 12, and 8. Well, in this case, you swap these two, and you end up with 12, 10, and 8. Okay? But of course, when you do so, say, you don't know what is below this, and you don't know what is below this. But 8 was larger than any of the numbers below 8, so you don't have problems here, because, well, the max property is still true. While on the other side, well, the side where you swapped the keys, well, you don't know, because the only thing you were sure about was that all the entries below were, say, less than or equal to 12. So it might be, for example, that here you had, say, 9, 7, and in this case, this will work. But in the general, for example, you might also have had, say, 11, and well, 11 would, say, break the max heap property. So the idea is that you do so, and then you start max heapifying this, which is max heapifying A at the largest. The largest was this one, okay, so in my example. Okay, so that is the working of the algorithm. Okay, now. Sorry, yes, here you mean. Yes, I was, yeah, of course, yes. Yeah. Yeah, this is the comparison between L and I, and this is the comparison between the largest of the two and R, yes. Okay, would you like to give it a try? Say with numbers, just to get an idea. Okay, so I'm not, that was, I mean, because my purpose was actually to go to the guys online and say the guys at the library and ask them to make this chapter available. So I took, well, I just went for another example. And so the example is, sorry, when we, this is a 2-hour lecture. So 90 minutes. So we will end at 11:50. Yeah, am I correct? Yes. So the array is this. Is 10, 20, 25, 16, 12, 5, 4, sorry, 12, 15, 4, and 6. Okay? So, first thing, represent this array as a binary tree, and then, well, this is not. And then maxify the root, which is, well, you'll see that 20, 10, 20, yeah, yes, you'll see that the root has the property for maxify, so it has both the left child and the right child to be max heaps. So the problem is with the root. So let's see what you can do with this. I think so. Yeah. Are you done? Would you like some more minutes? You are done? The others? What about you? It's okay? Okay, so we represented the array in, so it's 10, 20, 25, and then you have 16, 12, 15, and 5, and then 6. So yes, 20 is, well, this subtree is a max heap, because 20 is greater than 16 and 12, and 16 is greater than 6. This is a max heap as well. 25 is greater than 5 and 15. And so we can fix this by, say, calling max heapify with A1, okay? And, well, what we get is that we swap the entries here, and well, since the maximum, the largest value is this one, what we get out of, say, after this is 25, 20, 16, 12, and then we get 6, and here we get 10, and then 15, and then 5. And of course, this is not, I mean, we need to maxify this, and this is done by simply swapping 15 and 10. So the next step would be a call for maxify A. This is 1, 2, 3. And so we will have, again, 25, and then, well, I'm just, you get 15, 10, and 5. Okay, and this is the same. Okay, so this is the process that produces, say, fixes, in a sense, the structure of a heap where the property is not anymore true. Okay, so what is the time required for performing these operations? Well, you have a constant time, say, operation, which is the comparison between the three numbers, the root of the subtree and the root of, say, the index, and the two values, the two roots of the left subtree and the right subtree. And so this takes, say, constant time. And then you are going down in the, say, in the tree. So, well, in practice, you could say that essentially what you are doing is taking log, say, time, which is at worst proportional to h, but h is log n. H is the height of the tree, because at each step, in the worst case, you go one step and then one step below, and then and so on and so on. And so essentially this this algorithm performs in time big O of log n. And by the way, this I mean, in this of course can be proved rigorously, but well, actually, what you have to look at in the worst case scenario is how many, say, for how long you have to go down in the tree. And in the array you wrote above, there is a 4 instead of 5, being that the case we wouldn't be able to sort it, would we? A 4, oops, sorry. Was it a 4? I mean, so I wrote 5. No, probably my mistake. It's a 4. Well, it doesn't change too much, but no, it will be exactly the same. Actually, I mean, it was me. I mean, I took my own notes and I wasn't able to read it correctly. Actually, the 4 is a 4, but in the first, say, Yeah, I don't know why I wrote 5 on the whiteboard. No, why? What is well, the property is still true, even if there is a 4. Okay? Yes, please. Swapping this? Sorry, I don't understand the question. No, but because in that case, so if you have a 6 here and a 16 here, well, that would not be, I mean, the assumption, that's the reason why I wrote the assumption at the beginning. The assumption is that both the left subtree and the right subtree are max heaps. So you are not worried about what happens below, because you know that below everything is okay. So you're worried about only the roots, okay? And of course, you need to fix only the root, say the two of the, well, if of course if you swap the enters, because this is not necessarily the case, but if you swap, say, either with the left or the right, I mean, you have to then to look, say, to check for the correctness for the max property for the subtree for which you have changed the root. Yes. Yeah, it doesn't matter. I mean, but the assumption is that everything is already okay. So both the left and the right subtree are already they have the max heap property. Yeah, and yes, and that is what I'm about to tell you. I mean, because of course this is just part of the story, and then we will see how to. Well, essentially, this algorithm say uses effect which might or might not be already there in the heap. So now we need to look for a method for building a heap. Okay. And a method for building a heap, well, there is an algorithm which is it's called build max heap, and of course takes as an input just the array. And the algorithm is quite simple. It says for I that goes from a size divided by 2 down to 1, maybe, yes, it's 1, maxipify A1, AI, sorry. Well, the book goes into detailing the invariant, because of course it's a long process, but let's start with the main idea. So essentially, is the idea, your name is? Sorry? Nicola. So your idea is correct. You start from every entry in the arrays, that is every node in the tree, and then you maxipify that, and so you know that what's below is okay, and then you go up. The only, say, thing that is interesting is that you're not starting from the very end, but you're starting from the size divided by 2. So in our case, let's say, what was that? So let's say this. And say that we swap this as, what's your name? Sorry? As Davide suggested. Now, of course, we are not in the case for applying max heap. So 1, 2, 3, 4, 5, 6, 7, 8. So you see that the algorithm says start from here, 8 divided by 2. Okay? Why does it say so? Well, because for the way the max heap is built, starting from, say, 5 and going to the end, what you have is just leaves. Okay? So this is a leaf, this is a leaf, this is a leaf, this is a leaf. And any leaf, being a node with 0 children, is automatically a max heap, because it's greater than nothing. Any number is greater than nothing. And so you don't need to fix this, because as node themselves, or if you want to see them as subtrees, they are trivial subtrees, they are okay. So you have to start from here, because this is the only one that must be fixed. Well, the first one, and then you go from this, and of course you do what you do. Well, in this case you swap them, and then, well, in this case it's almost already fixed, so you don't have to do much work here. But that is the idea. That is the reason why we can start from there. Computationally, this means a slight advantage, because you are not starting from the very beginning. So again, I would like to give you another example. So to work on, slightly longer, but just to get the idea, because the other say, algorithms are quite easy to get, and so you have to get an idea of how, well, no. Let's start from this. So the array A is 4, 1, 3, 2, 16, 9, 10, 14, 8, 7. 3, 4, 5, 6, 7, 8, 9, 10. 4, 1, 3, 2, 16, 9, 10, 14, 8, 7. This is an example taken from the book. Okay? So first, you just sketch you write the tree corresponding to this, and then try to go up using build max heap. You'll need exactly 1, 2, 3, 4, 5 steps. Are you done? Yeah? Are you done? Okay, so, well, the starting point is this. We have 4, 1, 3, and then we have 2, 16, 7, 14, 8, and say below 3 there is 9 and 10. Okay, and so there are 10. The size is 10, and so we start from 16, which is 1, 2, 3, 4, 5, 10 divided by 2. And so we start fixing this. And to fix this, well, I do something you cannot do. I mean, 7 and 16. No, sorry, that's okay. Sorry, 16 and 7 is okay. So this is already okay, but this is not, because here you have 2, and 2 is less than 14. So we need to swap the 2 and the 14, and so we get a 14 here, and then we get 2. And then we move up to 3, which is again not in the right place. So we swap 3 with 10. And so we have 10, 9, 3. And then we have 1, this one, which has 14 and 16 below. So we swap with 16, and we have 16 here and 1 here. Sorry, and 1 here. So this is the next step. And of course, when we do this, now we are, we must do another maxipify because 1 is less than 7. So we get 7 here and 1 here, okay? And then we swap the 4 and the 16. Sorry? Echo. From myself or someone else? Sorry? Ah, okay. And then you have to swap 4 and 16, which are not in the right place. So again, you put a 16 here. But when you swap it with the 4, then unfortunately, you have to go back again. And so you swap the 4 here. You must swap the 4 here with the 14, and so the 4, you have 14 here, the 4 goes down here, and again, the 4 here is not in the right place because this 4 is less than 8, so you swap it with 8, you get 8 here, and you get 4 here. And then you are done, okay? So that is the process that allows for the building of MaxE. And essentially, well, first of all, how computationally, how can it go forward? What the last step you did? Which one? The swap between 4 and 8? You mean the swap between 4 and 8? It was 4 here and 8 here. And of course, you need to swap because 4 is less than 8 and it's not in the right place. So you need to fix this. And so you swap the root with the largest of the 2 children, which in this case is 8. So you get 8 here and you get 4 here. Yes, Daniel, Epify does that. Well, the maxipify actually is the procedure we are calling, say, starting from the, say, half of the size of the array and then going up. And of course, whenever you go down, I mean, maxipify in itself calls itself recursively. So you go down in the Maxipify say procedure. Okay. So so about, yes, please. I started, well, at the very beginning, I started from here. Well, the original tree was, what is it? This one. The original tree was 4, 1, 3, 2, 16, 9, 10, 14, 8, and 7. And I started from here. This is 16. I started from here because there are 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 entries in the array. The size is 10, so you start from 5. 1, 2, 3, 4, 5, which is the first one with the child. Okay, and so you start from this, and this is already in say okay, because it is greater than its only child, and then you move back. So you are moving back in this line. So you start with 2, and 2 is not in the right place because you have an 8 here. So you exchange this with 2, which I think is the thing that I did. And then you 3 again is not in the right place. So you gain, and then you have 1, which must be exchanged as well. No, sorry. This is not 4, it's 14. Sorry. It was 8 and 2. The problem is my bad writing. So it's 8 and 14. So you exchange the 2 with the 14. So you get 14 and 2. Sorry about that. Okay. Anyway, this example is taken from, if I succeed in getting you the chapter online, I mean, you'll get all the examples here. The only original thing, which is not original at all, but I mean, is the one with the numbers over there. That one, because all the examples in the book are using this array, and so, and again, so you start from here, then you go here, then you go here, then you go here, then you go here. You're going down to 1. So you are starting at a point, not at the end, because it's useless, because all the leaves are already maxipified already. So you start from the alpha of the tree, and then you go up, and then that is the way it goes. Okay. True, I missed the recursive part. Yes. Well, of course, these things should be, I mean, we are kind of dividing the two things between me and Professor Baldassi, but of course, a good idea would be to explain things and then implement it immediately after. Let's have a look at how this structure allows for an ordering algorithm. Well, no, sorry. Before we go on, just a word about the time complexity of this. Now, in principle, it looks that well, you start from here and you go up. So essentially, you are so you see that the algorithm repeats maxipify, n, the size of A is n, the number of nodes, n over 2 times. Which, so in theory, you should say, well, it should be big O of n, the number of times you repeat maxipify, times the time required for maxipify. Well, of course, this is true, because this is an upper bound. It's not a very tight upper bound, but you can actually do slightly better. The idea is, I'm just giving you the idea, the idea is, well, you can do better because the calls to Maxipify are actually going up. And say, as you go up, the number of nodes you have to look into are, say, less and less. Remember that Maxipify assumes that below there is a Maxi sub 3, okay? So you can slightly better this thing, and actually, this is actually not log n, but is, well, it decreases with as you go up in the tree. So in the multiplication between the two, this of course is measures kind of this, but this is actually decreasing, and because of this, essentially you get order of n. The details again are in the book, are essentially based on the fact that the number of nodes in any row, so at any height, is bounded by the size divided by 2 to the, say, the right power. So say, for example, in this case, we have n equals 10, okay? And then, say, for the nodes of, say, height 1, if you divide 10 by 2, you get 5, and this is an upper bound to the number of nodes you have here. If you are at height 2, then you divide 10 by 4, and you get 2.5, which is an upper bound to the number of nodes you get here. And at height 3, you divide 10 by 2 to the third, and you get 10 over 8, which is 1 point something. And again, this is an upper bound to the number of nodes. So you get the number of nodes decreases with kind of a power, say, below. And so the series actually converges. That's essentially the reason why you get a constant instead of getting log n. But anyway, as I said, these are details, mathematical details, and they require some time. So I want to go for instead to the, say, explanation of the heap sort algorithm, which is actually based on this, because once you have a heap, there is one thing you get for free, which is the maximum, okay? The maximum is the root node. So the heap sort algorithm works in this way. Where is it? Yeah. Of course, yes. So first of all, you build max heap. Of A. And then for I, that goes from the size of A down to 2, exchange AI, sorry, this is AI with A1. And then A size equals A size minus 1, and then Maxipify A1. I'm writing back this the same tree before, just to show you, and then I start commenting this. So it's 16 at the top, then you have 14, 10, 8, 7, 9, 3, 2, 4, 1. Yeah. So what does the algorithm do? Well, first of all, transfers the array into a heap, okay? And so you are now in a configuration possibly like this one. And then the first step, well, you start from the size. So you start from the last one. And you exchange the last one with the first one. You know that this is a max. You already know because of the structure of the max heap, okay? And so what you are doing is actually exchanging 16 with 1 in our case. So you get 16 here and 1 here. And of course, by doing this, you are completely destroying the max heap property. Well, in general, there are, say, of course you are destroying the property. But then, what you do is, well, so you are removing this. So you see that the next step, well, of course, one idea would be just take the maximum and remove it from the array, okay? But the advantage of working in this way, you get a sorted array in place. So you are not doing any, say, how can I say, any special operation on the array. The array stays where it is in memory, and you are just swapping two entries, two elements in the array, and taking the first, say, and swapping the first and the last. And so 16 comes here. And then what you do is, well, now I think, I pretend I'm not seeing 10 numbers, I'm just seeing 9 numbers. So the array ends here. And of course, this array is not now, is not the max heap property because of, well, we moved a 1 at the very beginning, but we can run the maxheapify function because the maxheapify works perfectly because, of course, this array, once you have removed this, is both subtrees are max heaps, okay? So you run maxheapify, and then, well, you have to rearrange, of course, for the numbers. And when you arrange for the numbers, then, well, you will end up with what? Let's see. So you get a 14, so 1 goes down. You get a 14 here. You get a 1, and then you swap 1, 8, and 7. You have 8 and 1, and then you have 4 and 1. You should get something like this. No. Eight, 4, 2, 7. Oops, my mistake. Sorry, guys. Yes, it was 8. It was 7, 8. Sorry, guys. It was 8, 7, 2, 4. That was 14. Yes, but 14 goes up. 8, 10, 8, 7, 2, 1. Yeah, it's okay. Yeah, it's okay. No, I was correct. So again, what happens now is that you have the maximum over there, which is 14, and now, of course, you swap 14 again with 1, with the least available. And so you get a 14 here, you get a 1 there, and then, well, the 1 goes to the right because 10 is greater than 8, and so and you go on with the idea, and so you output all the numbers in decreasing order, but they are in the right place. So at the end of the algorithm, you start with the lowest one, and you end up say the last one is the greatest one. Okay, so that is the way this works. Only a few minutes to the end. Giovanni is asking, why do we reduce the size, but then we should store A sub n somewhere before removing, isn't it? Got it now. Yes, that's exactly the thing. So you are not removing. First of all, you need the space, of course, to store it somewhere. But the advantage of doing this and working with the size is actually the fact that you are doing this in place. Think of an array, because essentially what you are doing is looking at an array. But you are looking at an array not using the proper indexing as the method. You are using the functions of the heap structure. But what you see in memory is an array, of course. So you are just changing the numbers, and then in the end you end up with this thing. Yes. So thank you, Pierluigi, for helping me in explaining this. So yes, that's an advantage of heap sort, because you build an in-place ordering of the array. Max heaps and min heaps are used for implementing priority queues. Priority queues are structures whose functions are not actually they are based on heaps. Priority queues are, well, very common in the real life. Like, for example, think of airplanes arriving at an airport or trying to land, and of course they arrive in order, and so essentially they get sort of a time. I mean, they arrive to land. But of course there are cases, and this is a queue, and it's called a priority queue because every so it's not just a structure, say, of like a normal queue, which is, say, first in, first out, kind of this thing, is a priority queue because every item also has a key as a value. Because, for example, you might have an airplane which, say, must land, say, immediately because of, I don't know, danger or something like that. And so you want to increase or decrease the priority queue so that actually you want to change the order. And essentially changing the order means changing, well, you build a priority queue using a structure like this, and changing the keys for the priority queue is equivalent to changing the numbers here, okay? And so the functions for priority queues are actually the functions here. Of course, when you change a number here, you are possibly, again, destroying the max heap property. So you need to rebuild the max heap property. And what you want to do also with the priority queue is then when say some of the plane, say the first plane lands, I mean, you want to remove it from the queue. And so you have an operation which removes say an entry from the queue. And there are say a number of operations and algorithms that are described there which perform this operation, but essentially they are based on the same idea here, okay, with some changes. For example, I will show you how can I say? Well, to find the maximum, so for example, let's say there is another plane that is going to arrive, if you want to insert, where did I have the insert procedure? I mean, where did I get it? Anyway, inserting an item into a new item into a heap, which means another plane is going to arrive at the airport, is just inserting a lead. You start with a lead and then you maxipify. So you take this number goes up, say in the proper way. Typically, in most applications, new entries are with the lower index, and then you move them up, so that you do not destroy the property, because if you typically you insert a number and this number is minus infinity for the machine, which is, say, a big number, the least number you can represent within the machine, and you put it here, well, the tree always has the maxi property because, well, any number is greater than minus infinity, okay? And then you change the key, and then you go up by fixing the property. So working with the priority queues is essentially working with heaps. I think we are done. 2 minutes over the end. So on Thursday, we will see something about binary search trees. Okay, and that will be. Okay, so thank you so much. And see you, actually see you tomorrow for the singular value decomposition. Bye, guys.